seen the half-wave dipole yesterday. So now we'll go with a validation of dipole antenna array. So the concept of antenna arrays is nothing but we are actually increasing the gain of the antennas based on which actually we may achieve the gain whatever we require. So basically, if you go with the nominal dipole antennas, in nominal dipole antennas, what happens is typically you may get somewhere around like 2.2 dB or 3 dB of gain. But if you want a high gain with the same dipole antenna structure, the way of doing it is we have to go for antenna arrays. So the concept of antenna arrays, so the concept of antenna arrays is nothing but we are actually increasing the gain and throughput through a constructive adding of your constructive adding nature of your antenna. So constructively, your radiation beams will increase in all the directions, and then you'll be actually getting a added up gain in both the directions. If you are going with dipole antenna, all the elements, like if you see the concept of Yagi-Uda antenna is also like dipole array only. So it's like dipole array itself. So here, this is the Yagi-Uda antenna, you can see. So here we have the parasitic elements, driven element, reflector element. So driven element and director element. Director elements are nothing but your parasitic elements. It doesn't have any charge. So I'll show you Yagi-Uda also. There you may have some idea. So this is how the Yagi-Uda antenna will look. This is nothing but your dipole antenna. This is a source of Yagi-Uda antenna. So you can see there is a cable here, and behind that, you can see a very big metallic element. This is nothing but reflector, and these are your director elements. So director elements will actually boost up your gain. So director element size is somewhat less when compared to driven element, and your reflector element is lengthier when compared to your dipole element. So this is also concept of arrays. So here also constructively we are improving the gain with respective number of director elements which we are adding up. So this is one of the concept of arrays. But usually antenna arrays, what exactly happens is, so usually antenna arrays, what exactly it does is the antenna arrays actually we'll be placing element one after the other. We have different modes of antenna arrays, like in dipole especially we have end fire and broadside. So how exactly this antenna array works is basically you are placing all the half wavelength dipoles or quarter wavelength dipoles in a specific distance. So this distance is also should be equal to lambda by 2. So because of this lambda by 2 distance, what happens is the antenna will radiate until a specific point, and here if I open the design, see, I have all the elements. All the elements are nothing but your dipole elements itself. So each and every element are spaced around with 150 mm. So if I open the design document, if you see, basically we are placing 11 dipole elements with 150 mm length apart. Each and everything are separated by 150 mm. So we are trying to radiate the antenna from 0.5 gigahertz to 1.5 gigahertz. The major area of concentration is nothing but your 1 gigahertz, where we are actually trying to work on with this particular antenna. But the sweep range, we want to put it from 0.5 gigahertz to 1.5 gigahertz. So you can see the distance between each and every element is 150 mm, and even the element length is also 150 mm. So lambda by 2 is 150 mm in the sense almost if you are calculating your frequency, if you're calculating lambda at 1 gigahertz, you'll be actually getting 300 mm. So you're computing by 2, so you're getting 150 mm here. So that's what we are trying to do here. So we have got the IGS file. So now let us just get started with the thing. So the pattern will be desperately improved actually with respect to this particular elements, whatever we are actually using it. So constructively, the radiation will be added up both in side lobe and the other lobe. So two sides will be getting the added up gain. So initially, when we have considered for half wavelength dipole, approximately we may get around like 2.26 dB or 2.3 dB or so. Now we'll be getting a higher gain. So now in order to get started with this particular thing, so we have got the IGS file format for this. So let us, and the complete IGS is treated as a one part. So this is nothing but dipoles, whatever you're treating. This complete part comes under a one part. Now we have to go to mesh window first. Under mesh window, now what exactly I'm trying to do is, I have to go to 1D. So I have to create mesh elements on my dipoles, whatever I have created. So go to 1D, click on curve, just like what we have did for your dipole antenna yesterday. And then here, go to element length. Element length, you put it as 30. Why exactly we are putting element length 30? Because basically we will be actually splitting your particular design in terms of lambda by 5, lambda by 7, lambda by 9, lambda by 10, lambda by 11. These are some of the representations, standard representations with which we'll be getting the accuracy. So here in this experiment, since the complete lambda is around like 300, so we are calculating lambda by 10 value. So since it's a dipole, we are going with lambda by 10. So let us go for element of 30 size and select all the curves. So in order to select all the curves, click on the curve first and then click on the environment, press Ctrl A, so that all the curves on the particular screen will be selected, or else you can select one after the other also. It's fine. So if you want to select one after the other also, it's fine, or else in the simple way, you can click on the curve, you can click on the screen, press Ctrl A to select all the things. So once you have selected all the things, let the element length be 30. Just click on generate 1D. So now we have got generate 1D part. So let us just click on apply. So once I click on apply, I will be actually getting my node elements. So I've got all the node elements. So this is fine. So this is the mesh step, what I need to do. I'm done with that. So you can also parallelly verify. So first step, going for curve, going for 1D, clicking on curve, set the element length to 30, that is 10 segments per lambda at 1 gigahertz. For 1 gigahertz, if I am calculating, I'll be getting lambda like 300 mm. So 10 segments I'm dividing it. So that's the reason I'm getting 30 divided by 10. So 300 divided by 10, 30 is a part. So then we have to click on generate 1D and click on apply. That's it. So we are done with this particular part. Now we have to go for SEM window. We have to go for tree views. We have to set it to field. And then we have to create a metallic wire with a radius of 1. And these are the nominal steps, whatever we follow. Go to SEM window. Under SEM window, go to view. Under view, we have SEM tree views. And set it up to E field FD. So once you are done with E field FD part, go to SEM window. Now you have to select your material editor. Click on material editor. Go to metallic wire. Each and every radius of a wire property should be 1 mm. So I'm giving 1 mm here. Click on apply. Close. So material will be available. Now you can also assign your material directly. Select your dipole, select your material, assign it. So you have to assign your material as well. So once you're done with the material assignment, click on close. Now the next property what we have to give is, we have to go for medium. Select your medium. Inside medium, actually now you are creating an exterior medium around your parts. So here you have to specify all the parts whatever are available in the design. So I have to just click on part. I'll be getting an arrow here. Click on this. I'll be getting a file menu. So if you click on this, it shows me the list of parts or number of parts, whatever are available. So click on the part which is available, click on OK, so that that part will get added up into parts list, and then click on apply. So now exterior medium will be created around your part. So around your part, the exterior medium is created. This is fine. Now we have to go for frequency. So frequency here I want to assign in a range. So I want to go ahead with interval. I want to start from 500 megahertz, that is 500 E6, to 1.5 gigahertz, that is 1.5 E9. And number of frequencies, here what I want to do is I want to go with 11. So if I click on add, I can see 500 megahertz, 600 megahertz, 700 megahertz, 800 megahertz, 900 megahertz, 1 giga, 1.1 giga, 1.1 giga, 1.2, 1.3, 1.4, 1.5. So we are running sweeping across this particular frequency range. So just click on apply. Now the frequency will get added up to your solution. So once this is done, now what we have to do is we have to go for source assignment. So under sources we have delta gap. Let us go for delta gap. Now the challenge is we have to create delta gap for all the dipole elements. All the dipole elements we have to radiate with the same power, so that I'll be getting a perfect pattern, perfect improved pattern as an array. So I have to create almost 11 delta gaps. So keep a track of it. So here you can see. So once if I select my node element, so you have to see the preview also. See, one. So one is nothing but it is exactly at the center. Okay, one is at the exact center. So click on OK. So node 1 is allocated. Here you can see Z direction has been defaultly given in this particular direction, and the source will be delta gap underscore 1. So first element is given with the source either in the positive direction or in the negative direction. It's fine. So we are exciting it in this particular direction. Now we have got this. Just click on apply. So see all other things. Always your E field direction should be yes. Okay, electrical field direction should be yes here. I'm trying to radiate in the Z direction basically. So that's how you have to radiate for your dipole antenna. So once this is done, click on apply. Now you have to give delta gap 2. So delta gap 2, go for the list. See, if I go for 8th pin, it is exactly at the center of second dipole element, whatever I have. So just double click on it. So 8 will be selected, and the direction is in the Z direction, and even E field direction is yes. Click on apply. So now I have got delta gap 2. Similarly, delta gap 3 now I want to assign. So go to node, same menu. Now go to 15. Yeah, 15 is exactly the center of this particular pole, whatever we have, right? So select that 15 and see the direction and click on apply. So once it is done, now go to so put it here. Now 22 is a next element for that. Double click on 22. You will be getting a node number of 22 here, and even the direction also you can have an observation. It's in same direction. So click on apply. So far we have got around like 4 delta gap sources. Now let us go for 29. Click on OK. So 29 will be allocated and click on apply. So we have got delta gap 5. Now let us go for 36. Double click on this 36. So the node will be allocated. Click on check the direction. Click on the apply. So we have got 6 sources. Again go to the limit. Now go to 42. 42 it's not the same. 43. So click on 43. 43 is exact center of this particular dipole antenna. So let us just go ahead with now this here. Now you can see we didn't get any direction here. So here also specified as 1. Okay, specified as 1. Then you'll get 1 second. Even node has been not picked up. Yeah, let us just double click on it. Yeah, 43 has been selected node. Now I've got it as in the positive direction. Click on apply. So we have got 7th delta gap source. Similarly, now let us go for 50. Click on OK. So for 50 also already you can see there is allocation in Z direction. Click on apply. And similarly 57. After that select 57, see the direction, click on apply. So done with this. Next, '64. Click on OK. See the direction. Click on apply. So we are done almost with 10 delta gaps. Now the last delta gap is left out. So 71. Click on OK. The direction is in positive Z direction. Click on apply. Close. So here we can see delta gap is from 1 to 11. So 11 delta gap sources have been assigned for all the. Now the sources are ready. Now what we have to do is we have to go ahead with the excitations. So in order to go for the excitations, you have to create separate excitations for each and everything. So we have to go about with a single excitation. Okay, before that also do this. Go to outputs. Under outputs, assign a far field sphere around your antenna. Far field sphere with 1 degree step. Put the power as yes, far field power, and click on apply. So now I have got a far field around my particular design. Now what I can do is I have to go for my single excitation. Here I have to assign 11 excitations for all the antennas, all the dipoles, whatever you have created in the array fashion. You have to go ahead with 11 excitations. So select the delta gap, click on assign, go with delta gap 1, click on apply. Okay, click on apply. So one excitation will be allocated. Second excitation, same. Right click on the delta gap, left click and right click on the delta gap. You'll be getting assign. Go to delta gap 2 and then apply. Okay, and apply. Similarly, left click and right click on the delta gap, assign delta gap 3. Okay, apply. Now delta gap 4, Okay, apply. Oh, sorry. Delta gap 5. Okay, and then apply. Similarly, delta gap 6. Okay, and then apply. So you have to create excitation sources for all the delta gaps. So once we create this, this will be available in the window. Delta gap 8. Okay, and apply. Delta gap 9. Okay, and apply. Delta gap 10. Okay, and apply. And then delta gap 11. Okay, and apply. So all the 11 excitations we have received it. So here now you can see excitation 1, excitation 2, excitation 3. So we have got 11 different excitations out here, right? So once you have got these excitations, then you can go for multiple source. Here we have multiple sources which are coming up, right? Multiple delta gap sources what we are using here. So since we are going with the array computation, there is a different step which will be added up. You have to go to SEM window. Under SEM window, we have array model. Go to array model. Under array model, we have array. Click on array. So since we are using a 1D array here, let it be 1D array itself. And since the projection you can see in the green arrow direction, we are placing all the elements. So that is nothing but you are placing all the elements in Y projection. So put dimension 1 data as Y as 1. So that means your array is in the Y direction. And similarly, number of elements what you have and the distance between each and every element is 150 mm. Number of elements what we have total is 11. So you can check with this step as well. So total number of elements you have to specify 11 here. And then we have to go for post computation combined results. So here I have to specify 11 elements. So this is how you will be actually configuring your array. Simple 1D array if you want to configure. This is one way of doing it. Then you have to click on apply. So once you are done with this particular apply, now the array computation model has been assigned to this. So now you have to go to array model and then go for combined results for array, because we have to see the combined effect of the array. It's not like I have to go for only single element response I want to see. I want to see the combined response. So in order to see the combined response, go to combined result of the array. Here we have to specify the angle. So theta angle, I'm specifying it as 90 degrees itself. And phi projection, you can go ahead. So phi projection, you can see here 0 to 90 with 10 degrees of step. So phi from 0 to 90 we are projecting, theta you are putting at 90 degrees and 90 degrees exactly. So theta comma phi directions, this is the main lobe where exactly we'll be getting the patterns. So why exactly in the phi direction, why exactly we want to monitor from 0 to 90 degrees is across this particular sweep we'll be actually getting your complete lobes. That's the reason we want to see the combined result in this particular direction. And it's always a best practice to reduce your reduce your coverage also. I mean, if you want to see your result coverage between this particular small range, it's very fastly computed. If you want to go ahead with the complete range, it takes a lot amount of time to compute it. So theta directly we are taking 90 degrees, exactly 90 degrees will be getting the response. And phi you can go ahead with 0 degrees to 90 degrees with 10 degrees of step. 10 degrees of step, just click on so 90 also I have to count it 0, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. So 10 will be sufficient. So 0, 0 degrees, 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 70, 80 and 90. Together you'll be getting 10 steps. So that's the reason I've put it as 10 steps. Then click on apply. So combined result also has been uploaded. And then once I click on my combined result, here I'll be getting my post computation. So under post computation, you can see I'm getting all my excitations, I'm getting my far field sphere, etc. So now we have to assign all the post computations. So 10 post computations, first antenna is taken as a reference. On that only we'll be visualizing the results, and the remaining all antennas we have to do the post computation and attach the result to the first antenna. So here we are getting 10 post computations by default. So what you have to do is let all the excitations be available. Go to far field sphere, click on this particular check on this particular symbol, right click, go to assign. Whatever far field sphere you have created, assign that. Okay, and then click on currents, whatever you want to visualize, click on apply. So post computation 1 is applied. Now in the same way, you have to go ahead with all the post computations. Go to post computation 2, the same procedure, tick mark on this far field sphere, right click, go to assign, select your far field sphere. So this procedure you have to repeat it for 10 times. Select the currents, click on apply. And similarly, post computation 3, far field sphere, assign far field sphere 1, click on OK, and then click on currents, click on apply. So this is done. Now post computation 4, go to far field, right click, click on assign far field sphere 1, okay, and then give the currents as well, click on apply. So the same procedure you should follow for all the 10 post computations whatever we have. So you shouldn't skip out any other computations here. If we are skipping out any other computations, maybe it results to some different results when compared to the original results what you will be getting it. Post computation 10, go to far field sphere, assign, click on far field sphere 1, okay, click on the currents, click on apply. So now we are done with all the post computations whatever are required. So once you got this, then what we have to do is we have to go to output parameters, go to final output. Here we are going with delta source, so all the things are available, and I'm going with delta and line source coupling. So admittance matrix, scattering matrix, I would like to get the results of this. So just select this, click on OK, and then go to SEM once again, output parameters, go to length unit, let it be in mm, click on apply. So this is done. Now we have to save the project. So we are done with all the steps. We can also check it once again from the SEM part. I'll also repeat it once again. So initially we have got the 11 elements. So we have selected all the elements and we have specified the length as 30, that is lambda by 10. So we have splitted the elements into 30 mm apart. So we are getting somewhere like lambda by 10 value, that is 30 mm. So we are getting n number of nodes after this. After this particular step, we went to SEM. We adjusted the SEM tree views to E field FD. And then material, I have created a metallic wire with a radius of 1. After that, I have used an exterior medium around my part list to create an exterior medium around my dipoles. After completion of this, I went to my part manager. I have assigned my metallic wire material to this particular dipoles. So once I'm done with this particular part, I have assigned my frequencies, that is from 0.5 gigahertz to 1.5 gigahertz in 11 steps. So together I have got from 500 megahertz to 1500 megahertz. I've saved it. And after that, now I have to create a delta gap source for each and every element, and setting all my E field DIRs to yes, and all the delta gap sources has the same value. Almost all the delta gap sources, whatever I have utilized, have the same value. So I have created delta gaps for 11 different surfaces, 11 different dipole elements, whatever I have. And then I have created a far field around my structure. After that, I have created the excitations. So 11 single excitations I have created it for each and every delta gap, whatever we have got. After that, we went to array model array. So I have opened this particular menu. I have set up the array configuration like array 1D, and even in y direction my array is spread out, so I specified it as 1. And bottom side I can see distance between each and every element is 150 and number of elements is 11, and starting from the reference element as 1. And then we have post computation array, where we have combined results for array. So once I click on combined results for array, once I have assigned my parameters of theta and phi, where exactly I want to see my combined results, the main lobe results. It started from 90 with 0 degrees to 90 from 90 degrees. So apart from that, so we have got this post computation window where we'll be actually getting the multiple sources. So as you see here, we have got the same post computation window. So in that we have got almost like 10 results. All the 10 results you should be assigning your far field along with your sources. That is what we have done. See, new 10 new post computation windows are created. In each window we have to assign create far field. That's it. We are done with this. So we have allocated the final output window, and then we have set up the length unit to mm. Then we have to save the project, and then we have to go for simulation. Now let us just do the same thing. File, save. Okay, wait a second. File, first go to save project, go to your desktop, go to your working directory. Just save your dipole array. Save your project in a specific directory, and then save the design as well. So once you save the design, the .vdb file will be saved into the design. So once we have got this, now let us go for SEM. Let us go for job manager. So we have got the exe path, working directory, and input file perfectly. Now let us just go for run. It will be solved in the basic MOM solver itself. So it takes a few moments to complete the things. Yeah, so we are done with this particular results. Now let us just try to visualize what exactly we are getting out of that particular results. Okay, so let us just open the file. Go to applications, go to visual viewer, and in visual viewer, go to your file, click on import and plot curves. Then select your file, whatever you have got it. Just go to your working directory wherever you have saved your file, dipole array. So dipole array.erfh5 file will be available. So load it, click on open. So we have got the file. So once you've got this particular thing, so let us just see the responses of this particular thing in later phase. Let us go for contour analysis. In contour analysis, you will be getting a wire currents, electrical wire currents. So in this way, we'll be actually getting a pattern. We'll be getting a pattern here. So we have to specify the different patterns out here. So we'll be getting different values out at different particular excitations. So you have to go for excitation 1, excitation 2, excitation 3, and you have to check all the excitations. So if you click on animation, if you click on excitation window, you can see all the excitation, all the excitations along with all the values out here. So we can get the responses based on the excitation value, whatever you're trying to give it. So how to verify all these things is, it's pretty simple. You have to go to excitation. You have to check the excitation, different excitations. If you go for excitation 2, that is a delta gap excitation 2. If you click on OK, you will be getting the results of delta gap excitation 2. You can see how exactly your excitation 2 is working at different frequencies. Okay, you can see the gain improved in different directions basically. So here we can compute for all the excitations whatever we have. Let us go for fourth excitation. In fourth excitation, I'll be getting a pattern like this. So it's like you are constructively improving your array pattern. You can see your gain has been improved a lot. So in both the direction, your gains are increasing. So this is how you'll be actually validating the results. So this is one sort of array what we are actually feeding it with. And there's some reflections also. So based on the frequency, based on the assignments, we are actually getting the reflections and the other parts. So in this way, you can go ahead with all the excitations. You can go one after the other excitations as well. So you will be getting the similar kind of pattern in the result window also, where he has only visualized only one pattern. So only one pattern has been present here. Okay, only one pattern is present here. So in that way, you can go ahead with multiple plottings and you can check it out how exactly it is working out. So here we can plot up all the different plots for all the fields for all the frequencies. I'll show you how exactly this could be done. So you can close this. Let us go for contour. Let us go for spherical grid. Okay. Let us go for 1 gigahertz because we have designed a frequency for 1 gigahertz. Let us just assign a gain here and then let us give a value of theta.
Rohit sir.
Yes sir, yes sir.
Is it like there is comparison with the Yagi antenna similar like this is coming now?
So it's a concept of array, sir. Basically, what happens is, if you're going with this is one sort of view actually. We have broadside arrays and end fire arrays. Okay.
Yeah.
So broadside arrays are nothing but we'll be placing all the elements side by side. Okay, we'll be using a spacing of lambda by 4 or lambda by 2 based on the structure what you're using, and then we'll excite all the antennas at the same position, through which what happens is actually each and every element will actually radiate a H-shaped pattern. Okay,
Yes.
so each and every element contributes a H-shaped pattern. So you're getting a beam at the left hand side, at the right hand side, which is covering the omni coverage. So since I've used multiple elements, constructively the directions in that directions your radiation patterns are getting added up. That's the reason you're getting a heavy coverage. Okay, in theta is equal to 90 degrees, you are getting a heavy coverage. So this is how you'll be actually getting this bidirectional patterns on the arrays actually. So here also what we did is we have actually used 11 elements. So each and every element has a delta gap source are excited in a same direction. So we are actually getting a pattern in the 8 shaped, exactly 8 shaped, which is actually because of all the repetitive elements what I've used with a proper spacing of lambda by 2. If I go with lambda by 4 also, it's fine. So you can see typical antenna lengths of the broadside array are from 2 lambda to 10 lambda wavelengths. Typical spacing would be lambda by 2 or lambda. So we are spacing in lambda by 2, and the feed points of dipoles are joined as shown in the figure. In reality, what happens is all the feed points will be joined together through one feed point will be actually feeding up all the antennas. Thereby, you will be getting a constructive addition and you'll be getting a broad beam coverage, broad beam of your antenna. So uh, it's like I can show you in the paint, sir, once.
But for the design point of view, sir, like let's say Yagi is also similar design, only reflector is coming.
Yes, sir. Yagi is also the same
Point.
concept, correct?
One
Right?
dipole, correct? Only one dipole.
Yes, yes.
According to the design or application point of view, which is the best? Because Yagi mostly they preferred, correct?
Yes, sir. Yes, sir.
This also giving the similar type of, only this has omnidirectional, both side is giving at least.
Yes, sir. Yagi is directional. This has omnidirectional coverage, sir.
Yeah.
The gain actually in Yagi, what happens is, sir, if you want to improve the gain,
Sir,
uh,
one more question. If one of the
yes, sir.
point, like let's say one of the dipole fails,
Yes,
by
sir.
that a student can analyze. Let's particular dipole don't have a feed or maybe feed damaged somehow.
Yes, sir.
Like physically wire connection disturb or something like that.
Yes,
So
sir.
how that will disturb? Is it theoretically will you get some problems, because some problem will be there, correct? And a student can analyze. It's not our, but they can do that, correct?
Yes, sir. Yes, sir. They can do that. I mean, what happens is actually, if you go for theoretical formula calculations also, sir, you will be actually getting some gain actually. So if one of the element is failing, the gain will be abruptly reduced. So you may understand that like one of the element in between has failed, which is acting as a reflector or so. If you, for example, if the excitation is not given and you're using a metallic wire there, what happens is this metallic wire or PECs, what they does is that they'll completely reflect it, sir.
Yes.
So if you're getting a reflection, then you will understand, okay, that element has been failed.
Yeah. I think they will
Yes.
test. Student they can
Yes.
test as assignment.
Yes, sir. Yes, sir. They can do that. This is a broad fire, sir, and you have end fire also. End fire in the sense it's nothing but you will be actually feeding in the opposite directions. So one time you will be feeding in the positive direction, the other side you will be feeding in the negative. So it's like you are feeding from end to end kind of thing. So this is a different orientation what we have, broadside and end fire. So end fire, it's like you're feeding in a different directions. Excitations, you're giving a positive Z direction and negative Z direction. Again positive Z and negative Z and so on. So here we'll be getting this kind of coverage. So from broadside, you're getting this kind of pattern, whatever we are visualizing now. From end fire, we'll be getting this kind of thing, sir. So you can see how exactly the elements are also placed. I'll zoom it up. You can observe. Yeah. So in end fire, you can see one is with positive excitation, one is negative excitation. So together you will be getting a pattern in this particular direction, sir. But whereas if you are going for broadside, like whatever we have did now, we'll be getting in this particular fashion. All the things are in the positive direction only. We will be getting in this particular fashion. So in our design also, we are getting in that particular in this particular fashion only. So this is how we have to validate it, sir. So once we are done with the design, we can check with all the excitations. You can see the gain has abruptly improved. Almost it's like 10 times of gain what we are getting it. 23 dB, 38 dB. So if you are perfectly resonating at a perfect frequency, at that particular frequency, you'll be getting a very good gain. So those observations, what we have to do. So here, if I want to plot all the parameters, what I can do is I can set up my fixed theta. I can click on plot. So I'll get a pattern here. In the similar fashion, what I can do is I can go with all the fields. So select your field 3 and then go with excitation 3. And then field 4 with excitation 4. And then go with field 5 with excitation 5. Field 6 with excitation 6. Field 7 with excitation 7. Field 8 with excitation 8. Field 9 with excitation 9. And then field 10 with excitation 10. So in this way, at a particular frequency, you can plot all the graphs. So you'll be getting lobes and the dimensions, whatever you're doing it. So almost it's like you can see the patterns are coming up like across like 20 to it's between 20 to 40 dB what we are getting here. So that's what you can visualize in the particular results also. Here we have to only limited number of parts, and even like gain has been swept around. So in this way, actually, we can set up all the parameters and we can visualize the results for each and every design, whatever we have done so far. So it's like if we are practicing it, and if we are doing a slight change in the design, or if you are going with your own measurements, you can also go ahead with a good understanding, and you'll get some good hands-on also. That's what is a major thing what we require. So
Rohit sir, one more question.
Yes, sir.
Like a feed element is a single point, correct? Which providing the all dipoles. And for testing point of view, we have a single channel, correct? We have to connect. Then
Yes, sir. Yes, sir.
going to we check the resultant gain or individual gains.
Okay, you are saying about resultant gain will be checking out, sir. For if you are going for dipole,
Yes.
especially dipole antenna array, you have to go for resultant gain basically instead of checking the individual gains. So in practical, what happens is, sir, whatever dipoles you will be having, right? You will be actually having some SMA ports or like coaxial probes for feeding it, right?
Yeah. Yes.
So we'll be actually using a splitter from a excitation thing, where we'll be splitting the channels to 8 or 11 based on the connections what we have, and then we'll excite it. So it's like you can excite it all at once, so that you'll be getting a pattern out there.
Okay.
Yeah.
So this is like a resultant one we have to analyze.
Whatever we are getting is like a resultant one only, sir. Correct.
Okay.
So is this clear? Like, is this clear? If you have any doubts, please post it in the chat box. We'll try to refer it once we are done with the other designs also. So we'll get started with the other design. I hope I'll share this document in the break time with sir. So sir will share with each and everyone. So can I move on to the next design, sir?
Students, is it any question is there?